So in the last video, I introduced this idea of limits and sort of showed you two examples where we were evaluate the limit of a function as the x-coordinate approached 5. And in one of those examples, it was really easy. All we had to do was plug in the number 5 and see that the output was 8. But I kind of argue that that's not the best way to do things, and to hopefully convince you of that fact, I gave you a second example where we couldn't plug in the number 5, and instead we had to look at x-coordinates close to 5 to figure things out. If you're like most students, you much preferred the first example and thought that was a lot easier, and it was, and you might be wondering, okay, how do I know if I have the first example or the second example? When can I just plug in a number to figure out a limit, and when do I have to evaluate the limit in this kind of strange way by looking at points close to it to figure out the limit? The answer to that question lies in the and continuity part of limits and continuity, the topic of this section. When can we just plug in 5 in quotes here to figure out a limit? And when do you have to do this annoying look at points around it kind of thing? The short answer is you can just plug in 5 if the function is continuous at the point 5. And without getting too deep into the minutia of continuity, I want you to kind of understand what this means for a function to be continuous at 5. So when is a function continuous? Well, this might seem stupid, but a function is continuous if it is not discontinuous. And you're like, you got to be kidding me. That's really going to be your definition? Well, that's going to be a good way to think about it. I can do a little bit better, though. A function is continuous if you can draw it, loosely speaking, without picking up your pencil. What am I talking about? I think it'll help to understand the 3 different types of discontinuity that we'll run into in calculus. One of them we've already seen. It's what's called a removable discontinuity, aka a hole. We saw it in the second example in the previous video, where you have an open circle like this. This function is discontinuous at this point 5. Because if I was trying to draw this graph, I'd be drawing it just fine, doing okay. And then when I got right here, I'd have to pick up my pencil, because there's that open circle, and then put it back down on the other side of that open circle and start drawing. This function is continuous everywhere except for 5. At 5, it has a discontinuity. That's not the only type of discontinuity. That's just the only one we've seen so far. But another type of discontinuity is seen in this second graph here. This might look like 2 functions, but really it's just one function with 2 different colors because of the graphing program that I used to graph it. If you were drawing this function, you'd be doing just fine, cruising along over here until you got to this point where x equals 1. It's hard to see, but the dot is filled in down here at 1. So if you put 1 into this machine, the number 1 would come out of this machine. However, when you put in numbers greater than 1, like 1.01 for example, the output jumps all the way up here to something close to 3. If you're drawing this function, you're doing just fine with your pencil down on the piece of paper, but then you got to pick up your pencil right here and start back over here to draw the rest of it. This function has a jump discontinuity, not a removable discontinuity, because it's not just an open circle, it's a complete jump to a different height. The height jumps from 1 to 3, loosely speaking, at this point 1. But really all you need to know is that this graph is discontinuous at the point x equals 1. The last type of discontinuity that you see in calculus is what's called an asymptotic discontinuity, and it's kind of like a special case of the jump discontinuity. I mean, it's fairly obvious that it's discontinuous, right? If you're drawing this thing, we're drawing, let's go down here. It goes down infinitely far, which is what this arrow indicates. And then all of a sudden it jumps up to the top up here. Ooh, jump. It sounds a lot like a jump discontinuity. Well, not quite. It's called an asymptotic discontinuity because there's what's called a vertical asymptote right here at x equals 1. You may have seen vertical asymptotes indicated with dotted lines in a previous class, so I'll throw that in there. The idea is, as my x value gets really close to 1, but is less than that, my y value gets infinitely far negative, really small, or really large negative if you want to think about it that way. And then when I jump over to the other side of 1, the height of my graph is really large positive. When I look at numbers slightly greater than 1, like 1.01 or 1.001, what comes out of my function are these huge numbers that you get infinitely large on the other side of this asymptote. My graph is clearly not continuous, but it's a little bit different than this jump discontinuity where my height jumped from 1 to 3. Loosely speaking, my height jumps from negative infinity to positive infinity. That's the case of an asymptotic discontinuity. But really, for our purposes, all you have to be able to see is that this graph is discontinuous. Specifically, it's discontinuous at 1. The important takeaway is that you can recognize discontinuities and that you understand that if the function is continuous, then evaluating the limit is super easy. If I have a function that's continuous at 5, for example, and you ask me to figure out the limit as x approaches 5 of that function, my answer is just f of 5. Just throw 5 into the function and see what comes out. That was this very first example. This graph is continuous at 5. There's no open circles, there's no jumps, there's no asymptotes. So to figure out the limit as x approaches 5, simple. Just plug in 5. 8 comes out, I'm done. However, this graph is not continuous at 5 because it has this removable discontinuity, this hole right here. So I cannot just go plugging in 5 into this function to figure out what comes out because I'll get this undefined output. When you're evaluating a limit at a discontinuity, evaluating that limit is a little bit more complicated. So in this video, I want you to understand the different types of discontinuities, and then also understand that if you're lucky enough to be asked to solve a limit at a point where the function is continuous, which is what is implied in this wording here, use continuity at x equals 4 to evaluate the limit as x approaches 4 of this huge mess, it's super easy. Just think about this thing like a function. I don't know, maybe I'll call it h of x just to give it a name. H of x would be the square root of 3x minus 8 plus 12 over x minus 1 divided by x squared plus x plus 1. I purposefully made this as ugly looking as I could so you'd think this would be a super hard problem. Because this function is continuous at x equals 4, which isn't even something you have to recognize at this point. You can just trust me since I said use continuity to evaluate this thing. Because we're continuous at 4, figuring out the limit is as simple as figuring out h of 4. Figuring out what comes out of this machine when I put 4 into it. And that's easy. Right? All I got to do is copy exactly what I see here, changing all the x's into 4s. So 3 times 4 is 12, and 12 minus 8 is 4. So I get the square root of 4 plus 12 divided by 4 minus 1. 4 minus 1 is 3, so I got 12 over 3. Divided by x squared plus x plus 1. Let's see, 4 squared is 16, plus 4 more is 20, plus 1 more is 21. The square root of 4 is 2. 12 thirds is 4. So I have 2 plus 4 over 21. In other words, 6 21sts, or if I really want to reduce fractions, 2 sevenths. When I put 4 into this ugly machine, 2 sevenths comes out, and because this function is continuous at x equals 4, the limit as x approaches 4 of this huge mess is just 2 sevenths. That's how we could evaluate this limit, and that will serve you really well for exactly one homework problem if I remember right. But again, we're not going to care about limits at points of continuity. So this is going to be kind of the outlier, the strange example, and the example that'll be a lot more familiar, a lot more useful to you will be examples like this guy where we couldn't just plug in 5 and had to look at points around 5.